Good morning, student. Today we discuss chapter number 7, equilibrium. Before starting that chapter, now let us clarify the term equilibrium. Student, equilibrium is a state of process in which the properties like temperature, pressure, concentration of a system do not change with passage of time. I repeat it again. Equilibrium is a state of process in which the properties like temperature, pressure, concentration do not change with passage of time. If the opposing process only involve physical changes, the equilibrium is said to be physical equilibrium. If the opposing process involving chemical change, the equilibrium is said to be chemical change. It should be noted the mixture of reactant and product at equilibrium is said to be equilibrium mixture. Now let us discuss equilibrium in a physical process. I repeat it again. Equilibrium in a physical process. Equilibrium in a physical process consists of following subparts. Number A1 is solid liquid equilibrium. In this type of equilibrium, both solid and liquid phases coexist. For example, H2O solid and H2O liquid coexist at 0 degree centigrade. In the second type is liquid vapor equilibrium. In liquid vapor equilibrium, both the liquid and vapor state coexist. For example, H2O liquid and H2O vapor coexist at 100 degrees centigrade. The third type is solid vapor equilibrium. In solid vapor equilibrium, both liquid and vapor phases coexist. For example, iodine solid coexist with iodine gas below the melting point of iodine. The fourth type of equilibrium involving physical process is solid solution equilibrium. Solid solution equilibrium. In this type of equilibrium, rate of dissolution of solid is equal to rate of precipitation in solution. For example, rate of dissolution of sugar is equal to rate of precipitation of sugar, then the system is said to be in solid solution equilibrium. Now the fifth type is gas solution equilibrium. Fifth type is gas solution equilibrium. In this type of equilibrium, gases dissolved in solution are with equilibrium with solution. For example, carbon dioxide gas, when dissolved in aerated drink, it is in equilibrium with solution. The solubility of gases in liquid can be explained on the basis of Henry's law. According to Henry's law, the mass of gas dissolved in the given mass of liquid is directly proportional to its pressure. That is, M is directly proportional to P. On removing proportionality sign, assign some constant, say Kh. Here the Kh is the Henry's constant. It should be noted larger the value of Kh, lower will be the solubility of gas in liquid. Henry law is applicable only if pressure is not too high, temperature is not too low, gas does not associate or disassociate in solvent, and also gas do not chemical react with solvent. The important application of Henry law is number 1, the solubility of carbon dioxide increases in aerated drink is based on Henry law. To increase the solubility of carbon dioxide in aerated drink, the bottles are sealed under high pressure. People live at high altitude, become weak and unable to think properly due to less concentration of oxygen there. The syndrome of such situation is called anoxia. These are the some applications of Henry law. Now let us discuss general characteristic of equilibrium involving physical process. Number 1. At equilibrium, some observable property of system became constant. Number 2. Equilibrium only involving gases can be attained in a closed vessel. It should be noted, equilibrium involving gases only attained in a closed vessel. Number 3. Equilibrium is a dynamic but a stable condition. Number 4. At equilibrium, the concentration of different substances become constant at constant temperature. Now let us discuss equilibrium in chemical process. Equilibrium in chemical process. The process is said to be in chemical equilibrium when the rate of forward reaction is equal to the rate of reverse reaction. Now let us discuss some characteristics of chemical equilibrium. Number 1. At equilibrium, the concentration of each of the reactant and product become constant. In chemical equilibrium, the concentration of reactant and product become constant. If we plot a graph between the rate versus time, we will obtain this type of graph which shows that equilibrium is a condition at which the rate of forward reaction is equal to rate of reverse reaction. So it indicates reactants and it indicates product. When the rate become equal, the state is said to be in equilibrium. So at equilibrium, the rate of forward reaction is equal to rate of reverse reactions. Now let us consider number 3rd. In third case, a chemical equilibrium can be established only if none of the product is allowed to escape out or separate out as solid. And number 4, chemical equilibrium can be attained in either direction and the catalyst does not alter the state of chemical equilibrium. Here one thing must be noted, if the graph indicates the concentration of reactant decreases, that means it indicates forward direction also and it indicates reverse direction also. The state at which both the rate of forward reaction is equal to rate of reverse reaction, the state is called equilibrium. So at equilibrium, the rate of forward reaction is equal to the rate of reverse reaction.